Last time we talked a bit about super quantum mechanics, and I gave you an example of a super quantum mechanical system. Just a couple of clarifying notes from last time that I was made aware of afterwards. Last time I wrote down some commutators and anti-commutators that corresponded to this supersymmetry algebra. We had usual Hamiltonian, which is the thing that governs time evolution. And in addition to the Hamiltonian, we had two fermionic operators, Q and Q bar. Q bar is the adjoint of Q, H is self-adjoint. And the really powerful relation is that the anti-commutator of Q and Q bar is the Hamiltonian. One point that I sort of implicitly used but didn't explicitly state was that Q and Q dagger anti-commute with themselves. So I've written that in here in red to illustrate that. I apologize for forgetting to write that down. Okay, so the first example that we saw of a super quantum mechanical system was this A-type quantum mechanics, where the data of such a theory was a Riemannian manifold M with metric G. We also chose a certain function from M to the reals called the superpotential, and for technical reasons, we chose it to be a Morse function. And then with this data, we can consider a classical mechanical system of a bosonic field, which is a map from the real line, our time line, to our target manifold M. And then we had two fermionic fields, psi and psi bar, that were sections of a pullback of the complexified tangent bundle of M. And I'm not going to write the action down again. It's essentially a supersymmetrization of the usual sigma model action. There were also some questions that were sort of motivating why, or asking where that action came from. And there's a really slick way of packaging these fields together. In particular, the data of this X, psi, and psi bar can be combined into a map of supermanifolds from R1/2 to our bosonic manifold M. Essentially, these fermionic fields, psi and psi bar, correspond to the fermionic parts of this map, and X corresponds to the bosonic part of the map. And there's a slick way of writing down the action that I wrote down yesterday on superspace as an integral over this supermanifold. And it's very cute. If you'd like to see it sometime, I'd be happy to tell you. The Clay Mathematics Institute book on mirror symmetry also does a great job in the two-dimensional setting, but it's easy to reduce it down to one dimension. That was the A-type quantum mechanical theory, or I guess the classical mechanical theory. When we quantized it, we saw we had a Hilbert space that looked like L2 normalizable forms on our target manifold. When the superpotential H was 0 and our manifold M was compact, we found that the supersymmetry generators, Q and Q bar, could be identified with the de Rham differential and the co-differential. The Hamiltonian was then the Laplace-Beltrami operator acting on differential forms. The supersymmetric ground states, or the zero energy states in this Hilbert space, were then identified with harmonic forms. Those are things killed by the Laplace operator, which in turn was identified with the cohomology, de Rham cohomology on our manifold, which is also equivalent to the topological cohomology of our manifold. And there was also some various statements about deformation invariance, namely these supersymmetric ground states are very much independent of a lot of the data that goes into defining this thing. In particular, the metric G doesn't show up in the supersymmetric ground states. This topological, these supersymmetric ground states are in some sense topological on the target. And so today, I wanted to start off by telling you a gauge theoretic enhancement of this target, or of this super quantum mechanical system. And I'm not going to be super explicit, but I'd be happy to tell you more afterwards. Again, this is pretty easily derived from this super space picture, but there's a little bit of work that goes into it, and I don't really want to spend a lot of time on it. Okay, so what would the gauge theory version of this setup look like? Well, we're going to have the same sort of basic data. We're going to have a Riemannian manifold, M. I'm going to use the same notation there. But let's suppose that we have a compact Lie group acting on our manifold by isometries. So it should preserve the metric, of course. And I'll assume that it's smooth and generated by some vector fields that I'm going to denote V sub I. And being a person who likes coordinates, you might write this as V A ddxa, where xa are the coordinates, some local coordinates on our manifold M. So if we have such a G action on our manifold M, we can attempt to gauge this symmetry and effectively look at some version of a quantum mechanical system into the quotient of M by G. I will write down a bit of the action here. I'll be a little lazy, so I hope you can forgive me. But the action looks as follows. We have the same sort of data. You have these fields x, psi, and psi bar. Those are going to be the same as last time. And the kinetic term is sort of what you expect. We take the covariant derivative of x. This d is going to be a covariant derivative for the action of G. So inside of here, there's our connection 1 form. In addition to our bosonic field X, that was a map from the real line to our target manifold, we're going to have another field that I'm going to call sigma. It's going to be a complex field valued in the complexified Lie algebra. Let me write that down here. Sigma is going to be a map from the real line to the complexified Lie algebra of G. Let me try to make it a little bit different from the metric. And it's going to be a complex field, so there's also going to be a sigma bar that corresponds to the complex conjugate field. So these are the usual kinetic terms for a bosonic scalar field in a bosonic complex scalar field. And then there are some potential energy terms. If we choose some basis of G, then we can decompose our sigma in terms of that basis. I'm going to write the components as sigma I. And there's a potential that looks like sigma dotted with our vector field V. And then we take the norm with our metric G. We also need to choose a metric on our Lie algebra, but okay. And then there's another kinetic term, or sorry, another potential energy term. I is it enumerates a basis of G. So this I and that I are the same I. No, VI is a vector field on our manifold. This is like, if I want to write sigma in components, I would write it as sigma I Ti, where this is a basis of our the algebra G. And what I've done here is I've contracted the components with the vector fields. Is that okay? All right. Okay, so then the last bit of the bosonic potential energy looks like a commutator of sigma with sigma bar. And then we take the norm of that. And then, of course, there's also fermionic fields that I'm going to be lazy and not write. So I'm going to write plus fermions. If you'd like to see the explicit part of that action, I'd be happy to tell you afterwards. But this is sort of the most interesting or most important part for us. The main things to see are that the like low energy solutions essentially look like having sigma valued in some torus. Namely, we have to have it, we can always gauge transform sigma to lie in some preferred torus of our Lie algebra G. And then we have this that sort of either says sigma is 0 or we're at a critical point on our manifold, or sorry, a fixed point on our manifold. And then zero energy solutions are also going to be constant, covariantly constant in time for both of these scalar fields. Okay, and given the time, we could go through the quantization problem and get our hands dirty, but I'm going to be lazy. The zero energy states are going to be very close to what we saw here, or at least some gauge theoretic version of it. And you can probably guess what it's going to be. In this case, we actually find that it's topological on the target and given by the G equivariant cohomology of M. We saw this yesterday in Chris's second talk, so I'm going to assume that you're familiar with it. The description he gave yesterday of the equivariant cohomology in terms of this de Rham model is essentially what you end up with here. Very roughly speaking, the differential Q bar looks like the de Rham differential plus sigma contracted with, or sigma times contraction with the vector field, V, vector fields. Okay, great. So that's the gauge theoretic version of this A-type quantum mechanics that we saw last time. It's sort of the natural thing that you would expect, or at least might expect or might hope comes out from this. Okay, so one important feature that physicists like to do is instead of requiring that our fields are actually dynamical, it's often useful to introduce background fields for these types of symmetries. Namely, we imagine that we don't have some kinetic term for our field sigma, but instead require it to be some constant value. And if we want to preserve supersymmetry, we more or less need to ensure that the potential energy of that field vanishes. So that's what I'm going to mention right now. These background gauge fields are sometimes called twisted masses in this context. So the basic statement is as follows. We can, but probably won't, turn on a background gauge field. We will have some background value for the complex scalars sigma I, and we won't turn on the fermionic fields either. But effectively, we replace the field sigma I by some chosen constant value M. If we want to preserve supersymmetry, this thing is required to be in the torus, or in some preferred torus of G, I guess complexified torus. where T is some chosen Cartan torus. And blackboard T is the Lie algebra or complexified Lie algebra of our group G. So the consequence of turning on such a background field can sort of be seen here. In particular, the low energy states are going to be localized so long as M is non-zero at the fixed points of the G action. In particular, we're going to have a potential energy given by the norm of M times the norm of the VIs. All right, I'll just write it like this. Should be using an eraser. MIV. And so minima of this potential energy are sort of zero energy configurations are going to be where these vector fields vanish, which of course correspond to fixed points of the T action on M. But this differential is pretty much the same thing as it was over there. We still have in this example where we turn on twisted masses, a differential of the form D plus M contract with the vector field VI. And because our minima or our minimum potential energy solutions are at fixed points of this torus action, we again get a version of the T equivariant cohomology now, because we only have sort of the torus part here. But crucially, this is a complex number. It's not some free parameter. So it's equivariant cohomology with the equivariant parameters specialized to the values MI. So over here, we would have different cohomology classes given by powers of sigma. If we have different powers of sigma in our cohomology class, then they're going to correspond to actually different cohomology classes. Whereas here, this is just some complex number or a set of complex numbers. And so we don't really need to distinguish different powers of M. That's sort of what it means to have specialize these parameters to some complex numbers. And when we're in the three-dimensional setting, these background twisted masses are going to be an important part in making sure that the system is gapped. In particular, this is another way, as compared to the superpotential that we saw over there, of making some compact target effectively, some non-compact target effectively compact. So if we had, for example, the real two-dimensional plane acted on by rotations, the fixed points are going to be a compact set. Oftentimes, this turning on of twisted masses effectively compactifies the target space to be something that's compact. Okay, so that's the gauge theoretic uplift of that A-type quantum mechanics we saw last time. The last version of quantum mechanical theory I want to mention is actually a special case of what we saw there. Let's suppose M is got a little bit more structure. Namely, it's actually a Kähler manifold. So we have that metric over there. If we also have a complex structure around that's compatible with the metric, our manifold scalar, and as a result, we can take that de Rham differential and split it into its del bar parts, or its Dolbeault parts. And the codifferential also has a similar splitting. And if we call Q bar plus del, Q bar minus del bar, Q plus is del dagger, Q minus del bar dagger. Then together with the Hamiltonian that we had over there, this gives us a 1D n equals 4 quantum mechanics. In particular, when we constrain our target space, we actually find that there's an enhancement in the supersymmetry. There's also generalizations of that Morse function that we saw before. If we want it to be compatible with this complex structure, we essentially want to choose a holomorphic function. So we can introduce a superpotential. In this case, I'm going to call it W. And it's going to be a holomorphic function from our Kähler manifold M to, well, C. And probably not super surprising, but in this case, these supercharges get deformed by the superpotential in sort of the expected way. Del goes to del plus del W wedge. And similarly for Q bar minus, this becomes del bar plus del bar W bar wedge, and so on. Where was the cutoff? I think it was right here. Is this far enough? Okay. So just as we saw over there, that our system sort of localized to the critical points of H. In this case, our theory will localize to the critical points of W. The equations del W equals 0 are often called an F-term equation. And I'll use that language next lecture as well. And then there's also a gauge theoretic version of this. That will play an important role in what we do next time, but I don't want to go into too much details right now because we'll see lots of it next time. But one thing I wanted to mention is that in addition to having this commutator type relation, we get another constraint on our supersymmetric ground states. In particular, they're going to localize to vanishing points of the moment map. We saw moment maps in several other lectures. We have some target space that has a symplectic form for sufficiently nice actions. There are moment maps that generate that action through Poisson bracket. And the gauge theoretic version localizes to the critical points of W as well as the vanishing set of our moment map. And there's also versions where moment map is not necessarily 0, but can have some central element on the right-hand side. And just in case you've seen these things before or never seen these things before but want to read up about them, This type of equation is often called a D-term equation. And the names come about because of historical reasons, but the F and D are certain fields that show up when you do this superspace description. In particular, there's an auxiliary field F, and solving the equations of motion for F will essentially set del W equals 0, and D is another auxiliary field now coming from the gauge multiplet that will set the moment map to 0 for some complex or to some central value. Okay, so one other bit of nomenclature, in case you've never seen this stuff before. When we have some collection of fields that transform within themselves under supersymmetry, physicists like to call these things more generally multiplets, namely if you have some symmetry acting on your system, fields that transform into one another in some fixed representation of your symmetry group are called a multiplet. And because this is a supersymmetry, we cleverly call this a super multiplet. So this x, psi, and psi bar are an example of one of these super multiplets. And similarly, the gauge field A, the fields sigma, and then their fermionic partners also form a type of super multiplet. The name that this one is given is sometimes called a real superfield, essentially because X is valued in some real target space M. And this multiplet where you have your gauge field A, your connection one form, and these sigmas and their fermions is sometimes called a vector superfield. Or super multiplet. Okay, so that's more or less the end of my escapade through super quantum mechanics. I guess one last thing that I'll get in trouble if I don't say is that there's another perspective on this type of super quantum mechanics pioneered by Witten in his revolutionary paper, Supersymmetric Quantum Mechanics and Morse Theory, where he relates this quantum mechanical construction to the Morse complex for this manifold M together with a Morse function H. And there's a very beautiful story where you have these critical points of H that are sort of the classical zero energy configurations, and then there's a beautiful discussion of tunneling that leads to the Morse complex that computes the homology of M. So I highly recommend that paper. It's exceptional. Okay. So before I move on, let me ask if there are any questions from those in the audience. If not, I'll move on to other things. Okay, great. So the next thing I want to introduce is a higher dimensional analog of some of the constructions that we were doing here. Namely, what we were seeing is that the zero energy solutions of our system, the zero energy states, could be realized by some cohomological construction where we take a preferred supercharge, in this case Q bar, and look at the cohomology of that supercharge. And this cohomological argument we talked about last time shows that the cohomology of Q is naturally identified with these zero energy states. And there's a higher dimensional version of this story that we'll be using in the coming lectures. So I wanted to give you a brief introduction to this notion of twisting a supersymmetric quantum field theory in general. And we'll see twisted quantum field theories galore next week. So the setup for those people to get home runs, I'm gonna give them a leg up. Okay, so what's the context? We're gonna imagine we have some supersymmetric quantum field theory in d dimensions. So what does that mean? Physicists usually consider theories that are invariant under Poincaré transformations. So that's some collection of rotations and translations. A supersymmetric quantum field theory in general is going to be an extension of that by fermionic operators in analogy to, or analogous to the ones that we saw here with quantum mechanics. In particular, we're going to consider the super Poincaré algebra. The Poincaré algebra has two sets of generators. The first ones I'm going to call M mu nu. This is an anti-symmetric two-index tensor that generates rotations. I'm mostly going to be talking about Euclidean quantum field theories because that's the natural place that twisting really happens. So it really is just rotations for me, but in the Lorentzian signature version of these theories, it's rotations and boosts, but I'm not going to stress that point too much. In addition to these rotations, we also have the momenta p mu. You can think of these as the angular momenta. This is the linear momenta. And these guys generate translations. And the new ingredient that gives us this super part of the Poincaré algebra, this right here is just Poincaré by itself. I guess I should probably call it the Euclidean algebra, but oh well. In addition to these bosonic generators, we're going to have some set of additional fermionic generators, and analogy with what I saw in the 1D setting, I'm going to call them Q. And there's going to have two types of indices. This alpha index, oh, green's not a good choice. This alpha index is going to be an index of the spin representation of our Poincaré group. In particular, this SOD rotation group has a twofold cover, the spin group, and this alpha index will correspond to a spinor index for the spin group. So alpha is a spinor index. In the three-dimensional setting that we're going to be interested in later, the rotation group is SO3, its spin group is SU2, and this alpha index is going to be an index for the fundamental representation of SU2. And yeah. Oh, sorry, yes, thank you so much. Oh, this is like a hyphen. Yeah, I'll do 1, 2, 3. Is that okay? Thank you. Okay, so alpha is a spinor index. I is going to be another type of index. It's going to go from 1 up to a number I'm going to call cal n. And when you see people, i.e. physicists, saying things like, I've got 4D n equals 2 supersymmetry, what they mean is I've got 2 spinors of supercharges. Of course, the spin group in various dimensions can be quite different. And so, for example, depending on whether there are like chiral spinners, you'll have more types of ends, but I'm not going to dwell too much on that. And these extra fermionic generators are called super translations. They generate super translations. And the most important relation satisfied by these things, well, M generates rotations. It's going to have brackets with the Q's that realize the representation of the spin group. The translations are going to bracket trivially with these Q's, and the Q's will bracket amongst themselves as follows. If I take QI alpha and QJ beta, where alpha and beta are again the spinor indices, and I and J are going to be these additional indices that enumerate how many supercharges I have. The bracket looks as follows. The two are going to anti-commute with one another if I is not the same as J. So there's a Kronecker delta there. And then there's the intertwiner between two spinners and a vector. In the SO3, SU2 case we're going to be interested in, these guys are going to be the usual Pauli matrices. And the two fermionic generators anti-commute to a translation. So last time, or with the one-dimensional setting that we saw before, Q might be written as Q1 plus I Q2. Q bar is Q1 minus I Q2. And then it takes the exact same form up here where QI, QJ, where I and J are 1 and 2. Again, that's why I had 1D n equals 2. This equals, well, there aren't really spinners, so that's why I don't have an alpha index. And we only really have one translation, the Hamiltonian H. So this is just a generalization of what we saw in super quantum mechanics to higher dimensions where there are more interesting symmetries of spacetime. We actually have rotations and in addition to the translations. Okay. So in the same way as we saw last time, there's going to be some distinguished supercharges Q that are going to be something that we can take cohomology with respect to. In particular, there's actually a variety of these things. And so let me explain what that is. Called the nilpotens variety. And it's going to be a subset or a sub of the space of fermionic generators. It's going to be the Q's. I'm going to call it like Blackboard bold Q, which is some linear combination of our supercharges Q. And we're going to say that the nilpotens variety is the linear combinations of supercharges that are nilpotent. They square to 0. These are the things that we can naturally try to do some cohomological games with in the coming lectures. And a couple things to mention. This variety has coordinates given by the Q's, and because of the structure of these anti-commutators, they essentially satisfy some relations, qi alpha, q j beta, gamma, mu alpha beta, delta ij equals 0. So it's some quadratic in this linear space. And it's often nice to do some projective version of this. We don't really want to consider q's that are actually 0. So we're going to assume that these qi's are not all 0. And we'll identify them by multiplication. So this is really some subvariety of a large projective space. So this is some explicit variety you can consider. Given some super Poincaré algebra, you can ask what is the variety of nilpotent supercharges and try to classify what they are in some context. I'll mention what it is in the context of 3D n equals 4 next time, or maybe even later, depending on how far I get, but probably next time. But given such a Q, we can attempt to take the Q twist. And just as we saw in the quantum mechanical setting, what this corresponds to is in some sense 2 parts. We restrict to observables that are Q invariant. So Q will kill these things, something like Q closed local operators. And we quotient by observables of the form O equals Q of something else. AKA, this Q twist is in some sense just looking at the Q cohomology of all sorts of observables in our theory. So just like in the quantum mechanical setting where we looked at the Q cohomology of states, we can do it also with local operators and extended operators, and that'll be this twist that we're talking about. Oh boy, so many things to say, so little time. Okay. The last thing I want to say about twists for now is an important characterization of the twist. Namely, we can consider the map bracket with Q, which goes from our super translations to translations. And we're interested in the dimension of the image of this map. This will tell us what types of supercharge or what types of translations are going to be trivial in cohomology. So suppose that we have some specific supercharge, Q mu, which will be some linear combination of the Q alpha i's that I had over there, such that the bracket of this Q mu with our twisting supercharge Q is equal to the translation mu for a given mu. Then what you can show is that Q closed operators O don't depend on the coordinate x mu up to q exact operators. And maybe I'll leave that as an exercise to show. It's essentially just using this bracket and realizing that p mu acts on operators as I times a derivative with respect to x mu. And the Q twist is called topological. If all p mu belong to the image of Q. In particular, local operators O don't depend on their insertion points. We're free to move them anywhere in space and it won't change any computation that we want to try to do. And then I guess for completeness, I'll also mention, but I won't write down, there are more general settings than just topological twists. We can imagine that this image isn't all of the p mu. The general situation is where we actually have some set of p mu being q exact, and other p mu only are q exact in some complex combination. So you'll have something that looks like p a plus I p a plus 1 being q exact rather than the p mu by itself. And so a general type of twist is called mixed or holomorphic topological. In particular, this looks like up to a factor of I, d by d za, where za is like xa plus I xa plus 1. Sorry, there should be a bar there. So in the general case, you have a system that will be topological in some subset of directions and holomorphic in the last ones. Okay. So I've run out of time. Let me just tell you where I'm going to be going next time. Next time, we're going to be looking at 3 dimensions, 3-dimensional n equals 4, quantum field theory. So let me just tell you what the 3D n equals 4 supersymmetry algebra looks like. It's going to, I mean, I kind of wrote it already. But there's going to be some supercharges, qi alpha, qj beta, where alpha and beta are fundamental indices for the SU2 rotating spacetime. I and j are going to run from 1 to 4. And the gamma matrices I wrote right there are the usual Pauli matrices that you are familiar with from quantum mechanics. One thing I should mention is that there's actually a symmetry that acts on the supercharges that rotates the I without touching the alpha and beta. And you can see that because of the fact that on by an orthogonal group, in this case, it's going to be SO4 because I've got 4 supercharges. And physicists love to decompose SO4 into 2 copies of SU2. And what we'll see next time is a convenient choice of notation. We split this I index into a fundamental index for these 2 SU2s. I'm going to call them A and A dot because of conventional reasons. If you've seen 4-dimensional spinners, that's probably pretty common. And the bracket of these guys is going to have this Kronecker delta turn into 2 Levi-Civita symbols. Like this. So this is the Levi-Civita antisymmetric tensor. This is sort of the SU2 tensor, SU2 invariant tensor that you can write down. And this is going to be the main subject of the next few lectures. So I'm now 1 minute over, so I should stop. Thank you for your attention. Sure, I'd be happy to take more time if you give it to me. Okay, so I think the natural thing to say now that I've given you the 3D n=4 supersymmetry algebra is to tell you some of the types of twists you can perform. As I was mentioning, space-time rotations and rotations of these I and j indices act on this nilpotence variety. And so you can ask for orbits of this nilpotence variety under this symmetry group. And so up to these rotations, I guess I should give this guy a name. This symmetry group that acts on the I indices is what's called the R symmetry. In the 1D n=2 case we saw last time, it was just a U1. In this case, it's an SO4 or 2 copies of SU2. But up to these space-time rotations and R symmetry rotations, there are 3 types of twists. There's a holomorphic topological twist. Again, there's lots of freedom in choosing which supercharge to take. And I'm going to choose the plus dot plus. Again, this alpha is alpha A and A dot are in some sense SU2 fundamental indices, and I'm using the plus and minus basis if you like. And this thing's often called the HT twist for holomorphic topological. And there are 2 topological twists. One convenient choice of them involves this HT supercharge plus extra bits. This one right here, where I take the plus and replace it by minus and minus, is sometimes called the A twist. And there's the second one where I change plus and plus dot to minus dot and minus. And this is what's called the B twist. There's lots of analogies between these A and B twists and the perhaps more familiar 2-dimensional A and B twists that you might be familiar with from other contexts. I can't really say a whole lot about that given the time. But the one other thing I will mention is that there's a mirror automorphism that acts on this algebra where we exchange the dotted indices and the undotted indices, or exchange these 2 factors of SU2. So if you have this automorphism, you can act on representations and things like that. We'll see next time. The super multiplets will be able to be exchanged. It's pretty easy to see that this will exchange the A and B twists. And again, this is called mirror symmetry for the same reason as in 2 dimensions. We'll see that there are going to be theories we can build, and this 3D mirror automorphism will act on theories in some interesting way, just as in 2-dimensional contexts. And they will be able to provide really cool mathematical consequences. I won't really get to say a whole lot about it, but it is just as exciting, or maybe just as exciting, depending on who you ask, as its 2-dimensional counterpart, 2-dimensional mirror symmetry. What makes sense to say? I think that's a natural stopping point because other things will take more than 3 minutes. So I think I'll just call it there. Thank you for the extra 7 minutes you gave me.